All right, thank you very much for the introduction. Welcome everyone, and thank you, Professor Matashi Sugiyama, for hosting my visit. Yes, so today I'm going to talk about graph transformer, and this is a joint work with Thomas Laurent, Joshua Banjo, Jan LeCun, and several other great collaborators. So let me start with the outline of the talk. So first, what I'm going to do is that I'm going to review quickly the development of graph neural network architectures. So where we are basically with this class of machine learning techniques. Then I'm going to talk about something important, which is the graph positional encoding, which is a way to augment the expressivity, but also generalization of these techniques. I'm going to talk about a transformer for sequences. So this is the natural applications of transformers. And then I will move to something that is interesting for us, which is graph transformers. So this is an architecture we developed in 2020. And now it has been used like a backbone for biology. There are still some limitations with graph transformers. So I'm going to show you how we can go beyond this limitation where we develop a graph visual transformer or MLP mixer. And I will conclude. So let's start. So neural network architecture. So if you want to do machine learning on deep learning plus X, basically you need three things, right? You need the data, you need your GPU, and you need neural networks. So there are today 4 classes of neural networks: convolutional neural networks, recurrent neural networks, and transformers. So CNN is developed for grids, for images. RNNs were developed for sequences like text, but also speech. And transformer has been designed for sets. So this is basically unordered element of vectors. So today the libraries have been developed for precisely for this class of architectures and data structures. So PyTorch, TensorFlow, everyone loves these libraries, but they are optimized precisely for that. The fourth class that have been developed is graph neural network. So it's more universal. It's a way to generalize actually any data domain, so it can be applied to more diverse applications. The problem with this is we are not GPU friendly. So because all our computations are actually for sparse linear algebra, and we don't have any GPU developed for that, so this is actually slower than the other techniques. So the GNN architecture, so what's a graph neural network? So this is actually a function. We call it an equivariant or invariant function. This is something that is invariant with respect to the permutation of the indices of the graph. It takes as an input graph topology and node and edge features, and is going to output some vector representation for nodes, edge, and graph. And you can use that for any downstream task, recommendation, visualization, whatever you want. So basically, people also call that a message passing process. So if you want to update the vector representation of the node at layer L to the next layer L+1, what you're going to do is that you're going to use information of the neighboring nodes and also edges. And this way you will be able to update the node vector. For the edge, basically you're going to use the current edge feature and also the node feature for the starting node and the ending nodes. Basically here you have all possible GNNs that exist in the literature. Okay, so you see it's very simple, and one paper is basically a decision of what is this node function and this edge function. Okay, so here I'm going to tell a brief history of graph neural network. So this is my personal view of that. So the first technique was developed in 2009, and I'm going to develop a little bit with the next slides. Then spectral GNNs, anisotropic GNNs, Westphaler-Lehman GNNs, and finally, I think we are in this era of graph transformer. So vanilla GNN, so that was developed actually in 2009 by a team from Italy. And in the paper, so that was before actually the deep learning revolution. I didn't know the paper when we started developing graph neural network. It came to our attention a bit later. But it's interesting because in the paper, we already have all the basic components of graph neural network. Everything was there, basically. So you have the equivariance, invariance with respect to index permutation. You are independent of the neighborhood size or the graph size. You have the local reception field. You have the weight sharing. The complexity is linear with respect to the number of nodes and the edge. So everything is there. The problem is when you look at the equation, is basically here you have a nonlinear activation. Here, this is your input feature, and this is your hidden representation. So if you know about RNN, you know basically this is some kind of RNN, not defined on a sequence, but defined on a graph. And we know RNN are actually not able to learn deep representation because they have the vanishing gradient problem. So it's something that has been an issue for a very long time. Okay. So it doesn't really work in practice. This is the point. So the first GNN that was able to produce some interesting results was actually spectral GNNs. So this is where I started working on that. So the idea was, before deep learning, I worked a lot on nonlinear graph spectral theory. And then when deep learning came, basically, I tried to find a way to do something because it was the quite exciting and new domain. So what I was doing at the time is I knew about how you do convolution on graph. There was no GNN, so we basically developed this way. So in graph vector theory, you can define convolution not on the spatial domain, on the physical domain, but in the Fourier domain, right? So the convolution between two functions on the graph is basically you take the Fourier transform of the two functions, right? So U is going to be the Laplacian eigenvectors. And then here you have your Laplacian, this is the spectrum, so this is the Laplacian eigenvalues. And then you learn basically a filter, a spectral filter that is going to give you the best possible accuracy. Okay, so this is learned by backpropagation. But at the end of the day, the only thing you do is basically everything in the Fourier domain. Okay, so it's still linear operations, but everything is done in the Fourier domain, and there is no issue for convolution. So to develop, so we have to make a choice for the spectral function. So we decided to use the Chebyshev function. So they are basically polynomials. And here you have your learnable function. Okay. So this is what we did in 2016. And then the year after, so that was Thomas Keefe and Maxwellin. Basically what they did the first order approximation of that. They say, oh, let's just use the linear approximation of that. And then this is now the most popular GNN, and I'm very jealous because what we should have done is exactly doing that. We should have just presented, the linear approximation and put in the appendix the complex stuff. But yeah, that is a good lesson for me. So basically, there is still a limitation. So when you do spectral operator, you know that basically the filter you are going to learn are going to be isotropic. So in any direction you are going to look at, they are going to have the same value. Okay, so this can be an issue because sometimes the neighbors have nothing to do to each other. Okay, so you want to differentiate this. So actually, I would claim that most data in the world, they are anisotropic, right? If you look at transportation map, a molecular graph, knowledge graph, everything is isotropic. Depending on the direction, you're going to have different kind of information. Okay. So after that, we started developing anisotropic GNN, so where the direction is important. Of course, you need to have an equivariant mechanism. So if you change the index of your graph, you still want to have the same vector representation for your node, your edge, and your graph. So we developed GTGCN in 2017. That was based basically on my PhD, using PDEs for anisotropic diffusion. So what you see here is just a discretization of what we call peronomaly. So that was a long technique that was used before deep learning, and it was doing just diffusion, but with some, you learn basically how you want to diffuse in each direction of the graph. Okay. And at the same time, there was GAT, so developed by Peter Velikovic and Yoshua Bengio. They use a softmax attention inside their network. So they develop at the same time as our model, but they get much more attention, for this. There are still limitations. So these techniques they have low expressivity, and I'm going to explain what it is in the next slide. And they have the oversquashing issue. So low expressivity, there are different ways to define expressivity for a class of functions. But here for graph, basically what we say is that they have low expressivity if they are not able to distinguish non-isomorphic graph. And I'm going back to that in the next slide. So basically, you see that these two graphs here, they look like very similar to each other, but they are not, of course. If you use GCN, Getty GCN, at the end, you will get a vector representation in a k-dimensional space that will be exactly the same. So you are not able to distinguish the two graphs. The same also, so if you want to count, for example, the number of cycles in a molecule, and also, or more generally, the clicks in a social network, this technique will not be able to count them. Okay, so they have a low expressivity in this sense. So people starting working on this graph isomorphism. So we know there is a lot of symmetry in graphs. We want to be able to distinguish, the graph which are the same and which are different. So what are graph isomorphisms? So if you have this molecule here, they look like different, but actually they are not. Okay, so if you give an index to each atom, okay, so here the fluor has 1, here the fluor has 5, and so on. So you can still find a one-to-one mapping between this index and this index here that will basically map this molecular graph to this one here. So they are the same. There are absolutely no difference. The only difference is that when you store in a computer the index of your node, they are going to have different values, but mathematically they are the same object. So we basically want a system that is able to say, oh, if they are the same, we want the same vectorial representation. If they are different, topologically different, we want two different vectors. Okay, so this problem of graph isomorphism, with knowing if two graphs are isomorphic to each other is actually, we don't know if it is NPR. It's weird. So even today, we don't know that. So this is a very interesting question. But of course, everything tends to say, yes, this is actually an NPR problem. So what Westphal-Lehmann did, so it was a long time ago in '68, basically they developed a very simple test. It was a necessary condition, but not sufficient. So it's not going to work all the time, to say that two graphs are isomorphic. For this, they are going to introduce what they call a coloring function. Okay. So the coloring function, what it's going to do is going to take, for example, one node here, Ci, I is 2, okay, and he's going to take also the neighbors. So the neighbors is going to be H, F, and H. And he's going to apply a coloring function. So he's going to produce a new color for C, okay? And you are going to repeat that many, many times, okay? So you start here, for example, this orange color is going to be the same as this one because C has the same neighbors, F, H, H, F, H, H. But after the first step of coloring, then this orange will have two different colors here, blue and here green. So you're going to have also different colors. So you apply this coloring process, okay? And at some point, you will not be able to produce new colors. The system, will stop, and it will give you an histogram of colors, okay? So if you can compare the histogram of colors of this graph here, and if they produce the same color, you say, oh, they are isomorphic with respect to the Westphal-Lehmann condition, which is not true anymore, which is not true all the time. So if you take, for example, this decalin molecular graph, this bicyclopentyl molecular graph, they are different topologically, as you can see. It's a very small difference, but the histogram of colors are the same. So Westphal-Lehmann condition is positive. So he would say, yeah, actually these two graphs are the same, which is not true. Okay. So very quickly, actually, you see that this Westphal-Lehmann, so we call it the 1WL test. So this is the original test, actually failed very, very quickly. So it's not a good measure of expressivity. But still, the community developed this gene network. So that was done in 2019 about the question, how powerful are graph neural networks? Okay. And then people quickly realized, oh, this is not enough. We need actually more expressivity, more colors. To get more colors, instead of only selecting for each node the neighbors, what we can select, actually, we can select hyper edges. So we can select, tuple of neighbors, not only 2, but 3, 4, and so on, k number as you want. So this way, you are going to be able to produce more colors, so you will be able to distinguish more non-isomorphic graphs. The problem with this is the price, the computational price that you need to pay. So a network that is KWL expressive basically is going to have n to the power k memory and speed complexity. So if you want to beat Gene, which is the original one, you need at least k equal to 3. So everything is cubic suddenly. And cubic is not something you can apply in practice, okay? So there's been some improvement on that. You can get quadratic complexity for memory, cubic for speed, but it's still too slow. And also something that we proved in this paper with Joshua Banjo was basically, it doesn't mean that even if you have more expressivity for your class of functions, it doesn't mean you're going to generalize. So there is always the question, what is the right inductive bias for generalization? And it's not because you are, a special inductive bias that gives you more expressivity that you are going to generalize. It's not true actually for this one. So, so the community took actually a little time, like 2 or 3 years, to realize that that was not the right way to define GNNs. Anyway, so the question is still back to, okay, so the original message passing GNN like GCN, GAT, basically they are limited in expressivity. So how do we improve expressivity? So as I said, this WHGNN is theoretically one way to do that. The other way, which is something that I pushed a lot in the community, was actually, okay, let's actually, what's the issue with GNN? The problem of a graph, an arbitrary graph, is that there is no notion of node ordering. You don't know where is up, down, left, and right for a graph. But you know that for a grid, for an image grid. In image grid, the top left pixel is always located at the same place, always. Okay, so for images, there is a natural canonical ordering of nodes, which is not the case for graph. So if we want to have basically in practice the same expressivity, what we need to do is to give a unique canonical ordering of the nodes of a graph, and then basically the system will behave much more, will be much more expressive and generalizable at the same time. So there has been some preliminary theorems about this. So for example, people say that if you take any node positional encoding, you can take, for example, just the ordering, just the indexing on your computer of the nodes, you already beat the 1WL test. And then here, this is a more general case, is that if you have a unique way to define the identity of your node, then you can show that they are Turing complete. So basically just pointing in the direction that this is interesting to have positional encoding. So there are two kinds of positional encoding. One is extrinsic. So if you do molecular or material science, you know the 3D position in the space, in the physical space. So this gives you a strong positional encoding. If you don't have this information, you can use structural positional encoding, for example, the Laplacian eigenvectors. So they map a graph into a k-dimensional Euclidean space. So this is also one way to get some positional encoding. So theory, the problem with that is theory say that, oh, it's good to have a positional encoding, but which one? So at the beginning, they tried something simple again. So each atom has an index. If you have n number of atoms, you have n factorial possible indexing, okay? If you want to generalize, you need your system to look at the n factorial indexing to be able to generalize. So this is not possible, right? You're gonna have a combinatorial explosion. So what are the properties to design a meaningful positional encoding? So the first one, you want uniqueness for each node. So you want to be able to disentangle each node. You want to have permutation invariance. So if you change the index value, you still want the same positional encoding, right? So this is important, again, if you want to generalize. You want also something which is distance sensitive. So the positional encoding, the distance between, for example, this atom here and this atom here should be proportional to the, for example, the shortest path between this node and this node here. So, and for example, if you have two close nodes, you want your positional encoding to be also to be close to each other. Okay, the distance should be close. So this is the three properties that we want. So based on this, basically we propose to use Laplacian eigenvectors. So they are, of course, very old technique that was used to do dimensionality reduction, right? So manifold dimensionality reduction. So this is a very old technique. But it's very interesting for what we need. So it's an hybrid system between positional and structural encoding. And it has everything. It's invariant with respect to index permutation. It's unique. It's distance sensitive. And actually, when you look at what people use in the transformer, which are the sine and the cosine functions, so the Laplacian eigenvector are precisely that. So if you take a sequence line, basically you're going to have your cosine and your sine function. So this is a generalization of what people did, you know, in transformer positional encoding, which, by the way, if you don't have this, it's not going to work well. So there is still limitation because Laplacian positional encodings are basically, this is a quadratic factorization. So the function that you have can be flipped in sign and it still give you the same factorization. So the system is ambiguous with respect to the orientation of the eigenvectors, if it is in this direction or this direction. So we need to force the system to learn this flip sign in some sense. So here we have much less. So if you have k numbers, so for example, k can be, you know, 9 or less. So this is basically the number of permutation that you will need to do. So in practice, despite this limitation, actually it works very well. So today, this is the most used positional encoding for graph. Okay, so in all papers, this is the one that we use by default in some sense. So this is using graph transformer and other techniques in GNN. Yes, of course, yes, please.
So why? Because there are three very popular graph Laplacian. So why do you use the symmetric normalized?
Also, it depends on your graph, of course. So
I mean, it's not necessary always to use this one.
Yeah, no, absolutely.
Sometimes you can also use the random walk version of unnormalized.
Okay, so this is another one that we also introduced. Yeah. So you can do the random walk one. So this is also one that we introduced. So this one has no issue with the sign. There is no problem with the sign. But the problem is that you may not have a unique representation for each node.
Yeah.
So the condition is basically you need to have a k-hop neighborhood, which is different for each node to have a unique representation. But you don't have, it's not anymore, you know,
in cluster and in like semi-space learning or something. Even so, the mathematics are very different, but the final performance are not so different.
No, they are very different. So depending on the task that you have, the data that you need, there is no magic bullet for positional encoding. So these two are basically the one that people use by default, the random walk and the Laplacian one. But people develop new ones that are better, you know, depending on their applications. So you need to have this inductive bias, this domain expertise to design a better graph positional encoding. Again, there is no like best one. That is not true.
I have another question.
Please.
So you give the example of application concerns chemical compounds. I wonder why like a graph is enough to represent the chemical compounds, because they are in 3D and the graphs are in 2D.
Yeah.
So the 3D structure doesn't matter, because if it's not a chemical compounds, very simple one. If it's protein, maybe the 3D structure would be very important.
Yeah. So for this, you will need a graph neural network. So basically, you need to be able to. So for example, for the protein folding problem, the AlphaFold. So AlphaFold is actually an edge transformer. So what it's trying to predict, it doesn't care about the absolute position of the position of the amino acid. What is very important is actually the relative distance between the residues. So what you want is basically how much distance do you have between different residues. So for this is actually better to have an edge feature and then improve the expressivity of the edge feature. So you can do that with an edge transformer, and this is exactly what they have.
Okay.
So
I think sometimes maybe it's not for protein or the simple chemical compound. Sometimes if you have some 3D structure in mathematics, you cannot use 2D format to represent them. Even if you add some edge feature on the graph, it's still like maybe.
But it's still in 3D. I don't understand. So the graph can be in 3D, right? So
okay.
I'm sorry, I don't understand.
Because
it's in 3D. So the feature that you have, the input one, they are, for example, the 3D positions. You can do that. There is no thing to stop you. So now what I want to say is that there is no absolute, best solution of representation. So you can use graph, for example, to solve the protein folding, and then the version 3 of AlphaFold get rid of that. Now they only do absolute position in 3D. So there is no like, you know, definite solution what you should use as a representation of your material, your molecule. It's basically dependent on the data that you have and the task that you want to solve. So, but I think it's important to say that. So here it's just techniques to give you a, you know, a starting point. Okay, that's it. And then you need to fine tune to your expertise.
Because all the simple graphs in your slides are in 2D.
Oh yeah, you know, of course. No, I
I
can put in any dimensions. It's just I cannot represent it. But yes, yes. No, absolutely. Yeah, maybe it's misleading. So, sorry about this, but yeah, don't worry. It can be generalized to anything, right? So it's kind of 3D here, what you have here. Anyway, thank you for the question. I think they are very important. Okay, so what we did then is to not only update the node, the edge, but also we can update the positional encoding. It gives you better results anyway. Okay, so now let me talk about transformer. Okay, so let's start with the standard one. So people started with recurrent neural network. So LSTM was for a very long time the dominant architecture if you have sequence of data. And I like it at the beginning. The contribution was interesting because suddenly you can generate a summary of your sequence and whatever the length of your sequence. It can be 10, it can be 1,000, 1,000,000, we don't care. So that was the idea of using a recurrence formula to do that. They use weight sharing, so you can do like million of steps. And that was a long time. But the problem is the limitation. So these systems, you can show that mathematically that they are non-linear dynamic systems. So for this, you know that any perturbation can amplify or can basically vanish. So this is a huge problem because you need to control the dynamic of these systems because so you don't want the explosion, you don't want also the vanishing stuff. So when I tried the first time coding this technique, I said, oh my God, this is not as stable. And I'm happy now we don't have to do RNN anymore. So they are very slow to train because you know that because of this recurrence equation, you need to go through this bottleneck when you do backpropagation. So it's very, very slow to train. And it actually is not able to learn very long-term dependencies. So nothing more than 50 steps can be learned in some sense. Okay, so now let me talk about something which is over-squashing, which is an issue for everything, not only GNN. So if you look at what is you know, CNN, RNN, GNN, you can represent this as with this equation. So if you want to update the vector, the hidden vector representation of the node I at the next layer, what you're going to do is that you are going to apply a function which will depend basically on some inductive bias, and the inductive bias will also depend on the domain structure. Okay, so if you have an image, basically the neighbors are going to be the pixel, you know, to the node I. If you are using RNN, the neighbor is just the word in the previous words. That's it. If you are using GNN, these are the nodes on your tree, for example. Here, this is a tree. And then you're gonna use the vector of I and all the vector of your neighbors, right? So it's true for any neural network, okay? Any neural network. So of course, sometimes what you want to do is basically you want to propagate the information from this node to this node here, or from this node of the graph to this node here. So because this stuff can only propagate the information by one hop, if the information that you need to be propagated is 10 hops, you need at least 10 number of layers. If you need 10 number of layers, it means that your reception field is going to grow with respect to the number of layers. So if you do CNN, it's going to be L squared because you're in 2 dimensions. If you do RNN, it's going to be L, and it's the number of layers. If you do GNN, you have this exponential explosion because you are going to look at the tree structure. So it's really huge. So the reception field of a GNN is huge. It's something that is going to consider a huge number of vectors, and maybe just 1 or 2 vectors are important for the decision. Okay, so this is not an overquestion. And again, this is not something that comes from GNN. This is actually identified by people for a long time. For example, in the original paper by Badano and Yoshua Benjo on the softmax attention, that was actually the test of time award this year at CLIA. Basically, there is this picture here. So if you use RNN, here this is the x-axis is going to be the sentence length. So you want to do translation. So this is 10 words, 20 words, and so on. The y-axis is the performance, the higher, the better. What you can see with the RNN is that it's going to work fine, but after 20 or 30 words, then you see the performance is going to decrease. And this is due to the over-squashing. It takes too much information to know what is the right one. If you use, here, this is a spoiler, but if you use the attention mechanism, basically you don't have any issue. So my point is, basically, RNN, but also GNN, they cannot stack too many layers because they are going to have to do some kind of average over a huge number of vectors. Okay. So the solution was basically transformer. Transformer, the idea is you want everything to communicate with everything in one step, in one hop. Okay, so that was the solution of the problem. To do that, they have to pay a price, which is the quadratic complexity of the attention mechanism. Okay, but basically it solved the problem of over-squashing and long-term interaction. So the key ingredient, you know that this is the attention mechanism. You have two kinds of attention mechanisms, self-attention, cross-attention. And then this is not enough. If you only use that, your system will never work, right? It will collapse. It will collapse to the trivial solution. So you need something else, like layer normalization. You want to control the range, residual connection for backpropagation, and a little bit that will give you 2 to 5% better an MLP just after the attention mechanism. And of course, you need to know which word is before which other word. So you basically are going to use some positional encoding, and the one community likes is the cosine and the sine function. More recently, there is the rotational positional encoding, which is basically doing dot product, which is a very nice idea. Anyway, so contribution, we solve over-squashing, we solve long-term communication, and suddenly we have a dynamic representation of the world, which is, I think, is the true success of transformer. So you want basically, depending on the context, to have different representation of your entity. So, for example, the word broke. The word broke has different meaning depending on the context. So the vase broke, the news broke, Sandy broke the law, and so on. So here, depending on the context, the vector representation of broke will change, which is very different from word to vec, which is fixed basically forever. The limitation of transformer is basically, again, as I said, this time the reception field is basically the whole sequence. Okay, so you need to pay the price of n squared. And basically, yeah, you need a good GPUs if you want to go to more than 1,000 elements in your sequence. And it's not enough. So if you use a transformer, it's something which is independent to which is invariant with respect to the ordering of your input vectors, right? So you need to have a positional encoding, and the positional encoding depends on the domain you want to apply it. So graph transformer. So what we did basically, it was in 2020. We say, oh, okay, so it looks like actually a good architecture, but what happens if you want to add edge feature, okay? And what kind of positional encoding you want to use for graph? So this is a very simple, I would say, mathematically simple architecture. And now today it's basically the backbone in biology. There are still the limitation over squashing and poor range dependencies. And I'm going to explain you with the last step of transformer how we solve this problem. Okay. So transformer, this is a standard one. So you have your multi-head attention, layer normalization, your hidden representation, the residual connection. Then you do a last step by using a MLP, a small MLP. Okay. For graph transformer, we had basically the topology. So you know at the core of transformer, you have the attention matrix, right? So what you do now is basically you hide some part of the attention matrix depending on the topology. So if this node is connected with the other nodes, fine, you keep it. If there is no connection, you put it to 0 or minus infinite if it is before the softmax. So you have this graph attention, this graph multi-head attention, which is here. And again, for the positional encoding, we use the Laplacian eigenvector as a natural generalization. So yeah, I don't think it's important.
Sorry, I have a question.
Yes, of course.
We can understand that in the sequential architecture, it's good to use positional encoding to the transformer because the transformer itself cannot calculate the position, such kind of information. But in the graph, do we really need such kind of position encoding? Because in the social media, such kind of graph, we do not have the this node is like the first node than this node, right? We do not need such information. So do we really need the Bayesian encoding?
So what you say is very important in social media. So you're already giving a context to the question. If you have only one graph, only one graph, the best positional encoding is the index of your node. And that's it. The solution is done. The positional encoding is only good if you want basically to be able to align the graph. Remember, for images, what we do with the natural positional encoding is the grid, right? The top left pixel is always the same for any images.
Yeah, like
exactly.
Like DFS.
Exactly. So if you have like different molecular graphs, you still want to align them.
Yes.
So you're going to use a kind of positional encoding to do that, Laplacian or whatever. If you have only one graph, the best positional encoding is the index.
Random.
It's random, but just take the index. And then you know basically that you're going to have a unique identity for each node. And it works very well. So you still need to have a unique identity because otherwise the system is equivalent with respect to the node ordering. So it's going to have a lot of confusion to make difference between different nodes. So you still need a unique identity for each node.
I see.
Okay, but you don't need something complex like the Laplacian eigenvector for one graph. Just take the node ordering. It's enough.
It makes sense.
Yeah. Thank you for the question. All right. Okay, so I'm gonna So something also for the people, for maybe the audience, if they want to try this graph transformer. So this is something you go on GitHub. There are instructions to install, and you can try, for example, using graph transformer without positional encoding. So this is a synthetic classification problem. The performance would be maybe, I don't remember, like 80%. But if you use the positional encoding for this kind of graph, so this is suddenly the performance will be 100%. So this is something important. The next step that we wanted to do, because it was for molecular prediction, was, of course, the molecule has edge feature. For example, the bond, right? The single bond, double bond, aromatic bond. All these bonds are important. So you want to be able to update the edge feature to make the best possible prediction, like the atom type. You start with an atom type, but you want to go deep representation to get the maximum expressivity. So we basically updated, we added basically the edge representation, and something that we did, there are of course 1,000 ways to add the edge representation inside your network. Here, what you see, you have a bilinear product, right? So this is the Q vector times a matrix, which is basically a diagonal matrix with the edge feature and then the vector key. Okay. Why we do that? The reason is simple: is that if suddenly your graph is fully connected and you don't have edge feature, basically the edge is 1, suddenly it gives you the standard transformer. So we wanted this mathematical consistency, because it's very natural things to do. So so that was the thing. Here this is also a simple way to apply graph transformer for molecular prediction. So you want to, I don't remember if it was prediction of solubility, I don't remember, but it's very easy to see how it works. Okay. Oh yeah, no, I don't have time to talk about this. So there are different ways to define graph transformer, different way where you can put your topological information. The one that works very, very well for molecule, and I was surprised, but this is good that people try, is basically using the shortest path. So you have your molecular graph, and then what you add as an extra feature in your attention matrix basically is the shortest path between the atoms. And of course, you add some learnable feature for this, but it's not so important. So it looks like the shortest path is actually a good inductive bias to improve the expressivity and the generalization. And people try, so this is nice. This is deep learning. People try different ways. So today, for molecular prediction, this is actually the best inductive bias for the graph transformer. Anyway, yes, please.
Did you by any chance check how discriminative this criterion is, like the shortest path? Because I can imagine that also just the number of molecules or so in the graph would be super important. Maybe if certain types or certain groups appear, so in the data set, it could probably be relevant to understand like how different are the actual shortest paths. So can you distinguish molecules based on that?
Probably this is the reason. I didn't do any analysis, which is a very good question, but I didn't do an analysis. But yes, probably this is very discriminative for different graphs. So in the case, I think here there was a case of predicting energy. That was actually an excellent inductive bias. So probably you're right. This is a way to distinguish different molecules depending on their energy that you want to predict. That's a good point. Yes, please.
This is jumping ahead, but you say like this oversquashing problem is being handled by the graph transformer, but I think graph transformer right now is mostly successful for small graphs, where in that case, I don't see why oversquashing might be such a big issue for GNN, because unless you have a line graph.
You're absolutely right. You're absolutely right. So the oversquashing doesn't exist for small graph. You're absolutely right. So here, yes, it's going to be the next slide. So basically, people try to do a little more than the small molecules. They do like protein, this kind of stuff. So it's like larger number of atoms, this kind of stuff. And then the oversquashing actually happens. But you're right. For small molecules, actually, you don't have this. Thank you. Okay, so so we have the archive, the GitHub, a blog post also which explain pretty nicely what's going on, and also into this library, the deep graph library. Okay, I don't want to go into this debate, so I'm sorry, I'm going to skip that because anyway. So now let me talk about exactly. So if your graph is actually larger than 40 atoms, for example. So basically when you have more. So this is exactly what happened also for transformer. So transformer at the beginning was used only for translation. Translation maximum is 100 words. Okay, so even if you have the n square complexity, it's fine. You can do translation, there is no issue. So with I would say with a standard GPU, you can do 1,000 tokens. Of course, the question is, we want to go much higher. If you look at a book is, I don't remember, like 30,000. I don't remember. So it's much more number of tokens than this. So how do we apply transformer when you have a book? So of course, the first thing you would do mathematically, you would do an approximation using a low rank, probably a low rank approximation of the attention matrix. That's the first thing to do, probably. And it's already used today. The other thing actually that was interesting is for images. So there is this visual transformer, also MLP mixer, but let's focus on the visual transformer. So the idea is, okay, if I want to make attention between this pixel here and this pixel here, the number, if I have my original attention matrix, if this is 1,000 pixel by 1,000 pixel, it means basically I would have an attention matrix of 1,000,000 by 1,000,000, million rows by 1,000,000 columns. So that would be not something we can do with our current GPUs. So what they did was very simple. They say, okay, let's actually cut the image domain into patches. Okay, so we cut into patches, and then suddenly to make the attention between this node, this pixel in this patch and this pixel in this patch is actually not that far in terms of patches. Okay, so we are going to perform the attention in the space of patches. So instead of doing n square number of pixels, it's going to be p square number of patches. Okay, so wow, the dimensionality, the complexity just drops a lot. So now, also the smart thing to do, I think, so you know about deep learning. Deep learning is when you have a small number of data points, the inductive bias is very, very, very important. Okay, you need the domain expert because you don't have enough points, to be able to learn something meaningful and then generalize. When you start getting to the large scale regime, actually, you want the inductive bias to be as light as possible because you want the number of data to be able to learn for you. So if your system is very complex, it will not be able to scale to billions of data points. It's not, this is LSTM, for example, it never worked. But if you do a very simple architecture like transformer, and you have a way to process millions of data points, then you win. So what they did here is that, okay, so they take the original image, cut it into patches, and then they represent the patch as not a word token, but as a visual token. And a token is a vector. So how do you go from a patch to a vector? You just apply a simple MLP. Okay, so you apply a simple linear transformation, and then you get one vector, Okay, so this is given here, and the vector is seen as a word. Okay, so you can apply the standard transformer architecture that was super successful for text, and then it works very well also for images. So again, so you take your image, you cut it, you apply an MLP. So by the way, when you apply an MLP here, here, and here, and you share the weights, actually you are doing a convolution, right? So this is the same, operation. The stride and the shift is basically the size of the patch, but this is a convolution. So the first layer is a convolutional layer. Basically, this is what you do, and the rest is basically transformer. So today, what Yanlu could say in practice is what you should do is actually not this. What you should do to get very, very fast is actually apply maybe 1,000 convolutional layer, and at the end you just apply a few attention layer. And this is in practice actually the best model. Okay, so this one is not the best, but that was for academia. Anyway, so you do that, and suddenly you can get access to the standard transformer. Okay, so of course we want to do the same when we have like larger molecules. So one application also which is very interesting is for when you have a cloud of points of billions, or let's say millions of points. So how do you apply graph transformer, right? Because you have too much points. So at the beginning, what I wanted to do with Xiaoxing, my student, I wanted to do actually a graph coarsening version, and then do at each level a transformer, just a transformer. And then I realized again, oh, that was going to be too complex for the paper to be accepted. So let's do only one layer of graph coarsening. And then I realized that was exactly what VIT did. So we wrote the paper like graph VIT to make it easier to be accepted. So here I'm going to show you only one layer of coarsening, but you can imagine to have multiple layers of coarsening. So if you have 1,000 nodes in your graph, one layer is one coarsening is enough. If you have 1,000,000, just apply 10 coarsening level. That would be exactly the same. There is no difference. Okay, so the difference between so the VIT was applying on images. We want to do graph VIT, so we want to apply on graph. So there are, of course, multiple challenges. Okay, so there are 4 challenges. So the first one is, okay, here we want to extract patches. So it's very easy for images because all images are the same size. Okay, so you can extract easily the same, patches. This is different for a graph. If you want to extract patches, they are going to have, different topology, different number of nodes. The next thing is, how do you tokenize? Okay, you need to go from the patch to the vector. How do you go from the patch graph to a vector? Okay, this is the next one. Here you don't have the same number of nodes, different topology. The next thing is the positional information. So for image, again, everything is not implicitly ordered, right? So this is the top, the top left. This is the top right, and so on. This is not the case for graph. We don't know where is the middle, where is up, where is down. So this is something we need to take care. How do we reduce overfitting? So there is something interesting with the VIT paper. The original VIT paper is that, so of course they need to compare with CNN. And the first data set you try is ImageNet. ImageNet is 1.2 million images. So they compare at the beginning with ImageNet, and VIT, actually, the performance is less than CNN. What they did to get the paper published, basically, is to add 10 times more images. And suddenly the performance was better than CNN, because we know that there are much more parameters to learn for a transformer than a CNN. Okay, we have the quadratic complexity, everything is actually much more. So there is something interesting is that if you want to use this transformer stuff, you know that actually you need much more training data than you would do it for the standard CNN. So this is exactly what they did, and then they were able to beat CNN, and they have the paper, very famous paper now, VIT. So, but the question is still also for us, how do we data augment for graph? And for graph, it's not clear also how you do data augmentation. Okay, so here we suggested something that works well, which I think is also one of the good contribution of the paper. Okay, so what we did is the same as VIT. It's just in the context of graph. So you take your original graph, you cut it into multiple, I would say, graph patch. Then you embed the graph patch using a GNN, you get vectors, and then the rest is basically transformer. Okay. that's basically the rest. So how do we do? Yes, you have a question?
Sorry, I was just wondering how important is it how you do the batching? So
Yes.
but probably you wanted to explain that next step.
Yes, absolutely. So for this one I need to remember, but today in some sense, so if we use so there are some libraries, professional libraries like Amazon, there is DGL. So the way you do the batching is very natural. So of course a graph is going to have different number of nodes. Okay, so you start with your adjacency matrix. Okay, but what you do is that you create a huge, let's say you have 10 graphs and each graph has different number of nodes. So what you're going to do is that you are going to create a fake adjacency matrix of, let's say, 1,000 nodes, and then you're going to have a block diagonal. And in each position of the diagonal, you're going to have different adjacency matrix of different size. Okay, and then when you apply the transformation A times H is a hidden feature. Basically, you are only going to use the information for each graph. This is how it is done for any professional library. Yeah, so you can, yeah, so yeah. Okay.
I'm a bit surprised because I would have expected something like that. You take one node. So you maybe randomly sample nodes, and then these are your ego networks or something like this, and then you take all neighbors of that node.
It is.
Them in this. But if you would do the diagonal, you might cut off neighbors that have a different index, right?
No. Maybe let me show you on the board. Yeah. So it's going to be much clearer after the talk.
Yes.
All right. So okay. So we have this. So of course I don't have much time, but so the first thing is how you do the patch extraction. So this is actually a very it's a long story doing graph partitioning. Okay. So it's an NPR problem. You need to find some compromise. The best that has been developed, I think, is Metis in the literature. Okay, so it's trying to maximize the association. So it's basically the number of connection you do in a cluster divided by the volume. So how many points you have. Okay, so but the problem with Metis is that it's only produced non-overlapping, and it's a deterministic process. And remember, you need to do data augmentation. So it's easy to solve the first problem. You just extract by k-hop. Okay, expand by k-hop. And for the deterministic one, you just perturb a little bit your graph, you apply Metis, you get the clusters, and you use actually the original topological graph. And it works very, very well. Patch encoding, so you use your favorite GNN, no over-squashing in this situation. Positional information, again, so you can use random walk or Laplacian eigenvector. And then you can use a standard multi-head attention or MLP mixer. It's not going to make a big difference. For the numerical experiment, so this is where it is interesting. Okay, so if you start, so for example, the one which are interesting is the peptide function and structure, because they have 1,000, I think 1,000, I don't remember 1,000 atoms, this kind of stuff. So you can see that if you use our technique, basically you are going to improve the performance, blah, 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 blah. It's not so. So one thing which is interesting is this over-squashing stuff. Okay, so here they design mathematically a data set to test how good is your GNN with respect to the over-squashing issue. And it's a very simple one, but I like it. So you have your root node. Okay, this is a binary tree, as you can see. And then you're going to have leaves. And then you can decide the depth, how much, levels of tree you're going to have. You see that for this one, at the end, you're going to attach a certain number of blue cycles. And this is a unique number of blue cycles for each node here. So for example, C has 2 blue. The root node has also 2 blue. And we want to know what is the label, which is C. Okay, so to get this information, you need to propagate the information from the root to the leaves. Okay, so you have to go through. When you do that, each time you are going to expand your reception field by 2, right? So it's an exponential, growth. So it's very interesting. So if you look at here, this is the number, this is the depth of the tree that you decide. So you just keep increasing, and this is the performance. 1 is 100%. If you see that all techniques, the GCN, the GAT, the GENE, whatever, they are going to fail very quickly. After 3 equal to 4 or 5 is going to break. For us, it's basically able to get to 7. Okay, so what happened is exactly that. Yeah, So we do the embedding, okay? And at the end here, basically everything is going to communicate with everything. So the graph patch are going to, all the graph patch are communicating to each other. Okay, so here there is only one level, but you can imagine to have actually, any number of hierarchical level, everything will communicate to each other. Vertically for the coarsening, and then horizontally for the nodes level. So basically it solved the problem of long range interaction. So we tried that for molecular. It's basically the state of the art today. Yeah, and I'm going to stop here. So development, so we started vanilla GNN, we went to spectral GNN, we started with that, but the filters are not anisotropic, they are all isotropic by mathematical definition. So we went to an isotropic one. Then the community decided to go theoretical with Wechsler-Lehmann GNN, but now they are correcting, it's not generalizable. Then we introduced graph transformer. He has a problem of over squashing and long range interaction. So we introduced graph VIT, and this is where we are, I think. What are the next? Yeah, so basically, yeah, so the problem also of GNNs, I think this is one of the problems of our community, is that we don't have good data set. And so, for example, for vision, they started with ImageNet. ImageNet forces the community to think to have good architectures. For an LP, they use internet. So it's a huge, for GNN, it's very small. So I think this is actually something that I try to push the community. So we have a paper benchmarking GNN and everything, say that our community is going to die if we don't have good data set. Also, one of the reasons we don't have a good data set is that, so there is academia and there is also industry. Industry also drives the research in any domain. So industry is not really interested in GNNs. The only industry in GNNs are biology today, because of AlphaFold and all this kind of stuff. But otherwise, I think the community is going to die at some point. So the way I see now is basically just helping a little bit, for example, this LLM stuff by, it's another talk, but basically using GNN to force the system to be regularized with the Wikipedia graph, for example. So it's going to decrease hallucination. But I think this is a huge problem for our community. And I think if we don't do anything, it's going to die in the next 5 years. Yeah, that's it. Thank you so much for your attention.
So I have one more question about the patch part. So in the original VIT, the patch doesn't have like overlaid actions, but in the graph VIT, there's some interactions between patches.
Yes.
Does it matter?
Yes, it matters. So you can see, for example, here. So if we apply Metis, basically it gives us, non-overlapping patches. Okay, so you will basically get 1, 2, 3. The edge also you will get 1, 2, 2, 3, but you will lose 3, 8, and 3, 4. So we want to increase this information. So it's fine. No, what we do, we just extend by 1 hop. So there's going to be a little bit of duplicate, right? So this patch will have 3, 4, 3, 8. This patch will have a 4, 3.
Yes.
But it actually improves the performance by 5% if you do that. So you don't lose, especially for small graph. For small, you don't want to lose any edge information. For large graphs, so again, this is the deep learning lesson. When everything is large scale, you don't care. But when everything is small scale, then you need to be careful. Yeah.
Okay. To be careful about the cutting.
Exactly, the cut is super important. If the bond in your molecule is very important, maybe this is a ring, a cycle, and you cut it, then maybe the performance is going to degrade a lot. So you just want to be sure you keep it.
So is that vulnerable? If we can write some kind of loss on the cutting.
Oh, we don't need to do that because the patch is already taking care of the of this edge. It just imagine that this is this extracted by Metis, and then you expand by 1 hop. That's the only thing you do. You expand by 1 hop. Okay, so this is it's actually my student is good. So so she put it here. You can see it. Yeah. So Metis only give you 1, 2, 3, but by 1 hop you get the others, right? The same 8 and 3.
Yeah.
Yeah.
So how do you really cut a graph into graph patches?
Oh, we use this guy. We use Metis. So it's a very standard technique. There is a huge literature on how you do graph partitioning.
Okay,
So it's basically, it's a combinatorial problem, right? So there are different ways to define this problem. So here what they want is find, for example, two clusters, and each cluster is going to have the maximum number of connections. So this is the association here and here, and divided by the volume, which is just the number of nodes. Okay, so the other one, which is very famous, is the cut. So instead of doing the association, you just want to minimize the cut. Here you maximize. The cut is basically how many connections between clusters you are going to cross. So they are the same. They are exactly the same.
Any spectral clustering technique?
Yes, can do the job. But the problem of spectral clustering is n-cube.
Ah, okay.
So this one Metis is n-log-n. So it's actually much faster.
Yeah.
But you're right. I mean, your favorite one is good enough. Yeah. Also, what is interesting with Metis again is that no, I think it's too much detail. Yeah. Go ahead.
I guess does it matter so much like which your partition function is?
That's a very good question. You still need a threshold of quality. So yes, if you do something very simple like greedy expansion, it's not going to give you actually good patches. You still need some kind of threshold of quality. So I work on graph partitioning for 4 years. So before doing deep learning, so the best one we develop is a nonlinear spectral clustering based on Chigurh and everything. Actually, you don't need that. We try. Metis is much. So Metis in the US is used everywhere in industry. If you have a graph, you want to partition the graph as fast as possible with the best quality, you use Metis. It's an hybrid system between coarsening, very fast, and then you do some kind of spectral clustering at the low level, and then you go back by refining. It's super fast, and it is the best trade-off. Everyone in industry in the US use Metis.
I have a question actually. Now that you have used Metis and you've got your graph partitioning in the transformer, do you still keep information about which of the patches are actually close to each other?
Yes, exactly. Absolutely. So we have this. So what you can do is you can apply, you can basically produce a coarsen adjacency matrix, right? Because you know the clusters. So it's very easy. It's there basically. And then on this, you can compute your Laplacian, your random walk, you get your positional encoding, so you know how far they are to each other. Yes. And you can do that as many level as you want.
This is still an important information of the transformer.
It is still an important information. So something that's also a very interesting question. So it's less important than the first one. This is also, we observe that. So if we do a Bayesian study, the first one, you need the positional encoding, otherwise everything breaks. Yeah. The second one, actually, you just gain maybe 5%, which is not much. So the information coming from below is actually already a lot, enough to get good performance. So my guess is that if you add one more, probably it's going to be 1%. Yeah, it's a very good question. Yeah, thank you. Yeah.
Question.
Yeah, go ahead, please. You go. I'm happy.
Let's see. One number of questions like for graph transformer, you're dealing with the overswitching problem, but I think one can also argue if you have a hub node and just make all the nodes connected to that and make everything two hub, then it kind of solves everything.
Oh, sorry. If you have one hub, you said?
Yeah, if you have like one node, like one synthetic node, and then you make all the.
Oh yes, I heard about this one. Yes, yeah. This is called a fake node, right? Something like that. Yes, I heard about this. So I think we tried a little bit. So it was depending. So what is the task for this? Because if you want to do, no, actually, I don't remember exactly the detail.
It's just it shows that transformers and GNNs can be equivalent. So any function that a transformer can represent can also be represented by the DNN with this extra node.
Yes, yeah. But that's an expressivity question. So not generalization question. Yes, yeah, I heard. Yeah, I heard about this. So I think today, to be frank, so I'm going to tell you what works in practice, actually. So what you need to do, and which was the best for application, like in industry. So you take a graph transformer, okay, and then if you have some special edge feature, you give, for example, the bound. You give the bound, okay. So a single, double, you give some feature, and then if you have no connection, you still give an artificial bound. Because for the transformer, actually, it's going to communicate the information. You do that, you don't have any more over squashing and long range problem. It works very, very well. So of course, you cannot do like 1,000 size of nodes. You still need to do some graph coarsening later. But this one already gives the best performance by far. So this is the one that works the best. Yeah. Yeah.
Can I ask
Please.
The first part about the positional encoding. Basically, if we regard the images, for example, images at the graph, grid graph, and each pixel has the edge between each surrounding pixel, and then apply the standard DNN, probably it's worse than the CNN, right? Because as you exactly said, that in the pixel case, the surrounding each pixel is not arbitrarily commutable. But if we treat it as a graph, it's commutable, right?
Yes.
And then probably I think that's why basically some student project does kind of exercises. But if you apply the very shallow CNN, like by applying the 3x3 convolutional network, the 5 layers have the higher accuracy than the 5-layer GCN or something. And then, but so take away from your talk, then if we add some positional encoding, like an index space or something, then that can solve this kind of gap between.
But you're talking about in images or talking about graph?
Images. Images are graph.
Yeah.
So,
as graph.
Yeah.
People did that.
Already?
Yes, people did that already, and actually gives better performance.
Okay.
Yes, yes.
So,
but it's more complex for the people to understand. I think this is why it's not mainstream.
That's a graph, but it's a more it's a position specific one.
Yes, exactly.
And then if we treat as just the abstraction by the node and the edges, and probably I think it loses some information.
Yes, absolutely. Yeah.
That's why my small question about the molecule is in between the free graph and the images.
Yeah.
It's a not arbitrary parameter, right?
I agree. No, I mean, it's if you add the edge information, so that you communicate between the patches, for example. So I mean, what transformer the attention metric does is actually learning this graph, right? So how much these patches are connected to each other, but it takes a long time for the transformer to understand what is the connection between two patches. So this is the attention matrix, right? It's trying to learn what is the best way. If you give a little push, for example, by having explicit edge feature, giving, for example, at the beginning some kind of distance between the patches, suddenly you boost the performance very quickly.
Yeah, my question is that, for example, positional encoding based on the Bresson something is basically graph theoretical, so it still loses some specificity.
Yes, absolutely.
Then can you have some concrete examples of position specific encoding by the
for images, you mean?
No, the molecules.
So I'm sorry. So what's the question? The question is how expressive are the Laplacian position encoding?
No. If we treat molecule as completely graph at the topology, abstraction by just as a graph, and then the graph means as we see in your example in slide, then that graph isomorphism problem. And then if we arbitrarily permute the graph, and then that's its same as a graph.
Yes.
But in the case of the molecules, the neighboring nodes is not arbitrarily permutable. So it's more similar to the images cases. The images that epsilon pixel. If we arbitrarily permute the epsilon pixel, then it loses the original information.
But you mean the positional encoding is not permutation invariant? This is what you mean?
Okay, so then in images case, it's probably if we add some index space position on.
Yeah, this is what I do.
solve, that's how about the molecular case? It's a not grid, so we need to handle the different number of.
Yeah, this is something I want you to do is you take your image and you do segmentation of your image because it's semantically more natural than the patches that are, arbitrary put here. So I wanted to just put the, extract the region by, they are fast algorithms to do that.
Okay,
So,
yeah,
but yeah. Let's talk more about this. I think I want to understand better. Yeah.
So deep stack of graph convolutional layers. Another solution is we just use the residual connection and some sort of rough normalization.
Yeah.
Like then, what do you think about the idea, or we use the transformer based architecture, or just uses a standard traditional graph layer with the residual connection, some sort of layer norm or something.
Yeah, maybe you can. So yes, it's a volume at the end, right? So you have the z-axis is going to be the coarsening level, and then xy is kind of the graph level. So I think, yeah, maybe you can do some kind of transformer in 3D. So you would have maybe the layer norm, the residual connection, not only on the physical domain, but also on the coarsening dimension.
Yes,
but today, I mean, yeah, we didn't try to go that deep. So yeah, that's a good question.
Some libraries I did paper of the 1,000 layers of this.
Yes.
Deeper GGN or something.
Okay.
And so in practice, it works well. But also, I thought transformer with traditional encoding might be work.
So this is something this is a very interesting question. So exactly. So we are trying also because transformer today has no hierarchical information. So today what we are also trying to work, it's an ongoing project, is to have some kind of hierarchical positional encoding because it's much faster.
Okay.
And this way you are able to communicate very far away also. And you can use some kind of n log n information for your transformer.
Yeah.
So this is something we are working on because this is unexploited today.
Yes, then long range communication is one of the problems. But I also encountered some over smoothing problem because if we apply the message passing on the local node, then I think if we, for example, if we stack the 10 layers of standard GCN, probably I think output feature is almost the same because
not with transformer. So this is true with the GCN.
Yeah, so
because the GCN doesn't have enough non-linearity. If you have enough non-linearity, you don't have the actually this problem. In practice, I've never seen the problem.
Okay.
I saw you can theoretically formulate it, develop experiments. In the real world, you never have this if you use transformer. Because the non-linearity is too strong. It's not possible to.
In transformer block, it's the free form plus the residual connection is layer number.
Yeah, exactly.
That's a free FF layer. So these layers can be replaced by GCN layer, for example. And
exactly.
It's kind of a transformer like, but it also regards some extension of standard GCN with the residual connection plus graph model. So
but GCN is just doing convolution.
Yeah.
So this way it's of course. No, but I mean the community has you can find, and all experiments are usually based on GCN. So that's why. But again, my experience in industry, this kind of stuff, no, you never have this issue. The problem is oversquashing. The issue is oversquashing by far. That's the thing we need to deal with.
Even for the convolutional or progressing without the normalization and the residual connection, progressing a maximum layer above, we can use as a key or something like that.
Yes.
So if we introduce the item of the resonance, then we can have a 2,000 layers.
Exactly. So you are mentioning this paper, 1,000 layer.
Yeah.
So we have a paper just before we didn't publish. It was just with a professor friend, so we don't go to. We just put on archive, and we say explicitly, as you said, So we put like 100 layers. Everything was, the performance was good. And then the author of the 1,000 layer, send out a paper, say, oh, you didn't cite our paper, this kind of stuff. And then I look at the date. I say, yeah, because we published the paper 1 year before you. So that's why we didn't cite your paper. So you're right. I mean, it's true. But yeah. It's again, the problem is the design. So if you are very careful with the design, the pitfalls. Basically, today we have the tools to get beyond. The only problem is the oversquashing, I would say. We need to be very careful about this one, but the rest is solved. The rest is solved. I don't see any issue with the rest.
Okay.
Oh, sorry. There's a question on the
Yes.
checkout. So the question is could you clarify the key difference between graph VIT and full connected hierarchical GAT? My impression is that the decision gap is whether the information is repeated or raised at successive supernode level, or is there a deeper difference between these two approaches?
So the difference between graph VIT and GAT, right?
Yeah.
Or hierarchical GAT, I think. So I don't know hierarchical GAT. I will need to see the difference. So GAT, first of all, is inspired by transformer, but it's not actually the exact formulation of transformer. There is no mathematical consistency between GAT and when you have full connection. And GAT also has basically no positional encoding. It has what else? No positional encoding. The edge feature? There is no edge feature in GAT. And the way you design also the attention mechanism, there is, I don't remember, but it's not exactly the same. So for example, what we did, we have a paper which is benchmarking GNN, and we compare, everything. So there is a gap between GAT and graph transformer and graph VIT. So the devil is in the detail, I would say. So you need to look at precisely, the difference. Question: can your method handle non-planar graphs? Yes, it can. So again, I think all this technique, graph transformer or variants, at the end, the only difference probably is going to be the graph positional encoding. So you need to have a graph positional encoding which is expressive and generalizable for the task that you are trying to solve. So Laplacian eigenvector or random walk are very kind of agnostic to the task. But later, so for example, we work in genomics. We wanted to reconstruct the human genome. So we have to define very specific graph positional encoding depending on the expertise of people from the domain to get good performance. So we didn't transform. We didn't change much the architecture. We make it more directed, but more or less this is the same architecture. What was a big difference is the graph positional encoding. So you need something. You need expertise here to make a big difference. So I think if you want to handle non-planar graph for a specific application, this is where the mathematics or the domain expert is going to be very important.
Go ahead.
You see graph transformer being useful for node level tasks as well, because I think the data limitations and not being able to deal with very large graph, those are probably not the main bottlenecks of it being.
Yeah. So for graph transformer, you're in the context of small graph, in biological graph. This is why I say this is where the success is. There is no success beyond that. And of course, what the system is doing is give you a deep representation of the node feature and the edge feature. So if you want to do like a node prediction, there will be no issue, because this is what is learning, basically, to have a very, at the end, so you have your L transformer blocks, graph transformer blocks, and the last layer is basically some predictive layer for your downstream task. For example, you want to predict the energy of the molecule, so you will do a mean over the node features. If you want to predict maybe the atom type or whatever, if you want to predict something related to the atom energy, for example, so you would do an MLP for that you apply on the node feature, and you share it for all the nodes. So any GNN basically is learning a deep representation of the node and the edge. At the end, this is what you want to do. If you have a large graph, today all message passing GNNs are not going to work. You need to add a layer of coarsening if you want to make them work. That's the issue. So the same with transformer, I would say. So today, I don't know exactly what is inside the Gemini, OpenAI, transformer. They say, oh, we can do a 1 million window context. What does it mean? How they do it, right? So that's also a question, right? Do they use a low rank approximation, or do they use some kind of coarsening? As I said before,
very special data structure, some tree-like data structure to reduce the computational complexity.
For LLM, you are talking about?
For like you mentioned 1 million
yes
context window. They are using many different kind of tree structure, very deep, very special data structure. So the recent study about the attention really going back to the nature of computer science.
But what do you mean? So, for example, I can decide to put all archive paper, or maybe 1,000 archive paper as a context window for Gemini or OpenAI, ChatGPT, whatever. You said they use a special data structure. What do you mean by that?
But in like a DeepSeek and other Chinese large models.
So how they do it? How they are able to get 1 million window context?
I can see that they use some technique from the original computer science and the data information retrieval and like AI. They don't really search over they don't really search over all the context windows.
Okay. So but this technique, it's in some sense it's agnostic to the domain. So I can imagine that maybe tomorrow someone is going to take this idea for graph. There is nothing maybe that can stop doing that. It's
to apply techniques to graph.
Yeah. The issue is not mathematical, I think. The issue is really what kind of applications, and data set people in the GNN community would need.
AI is not accurate, it's approximate. So it's like the first, for example, if they want to translate something, translate a Chinese novel into English, everybody. What they are looking
I like this one.
If I want to have the first section or the first paragraph, I don't need to look at all the context window or all the original Chinese book to know it, because even if the context window is very long, it's one input and one output. But I know if I am generating the first paragraph in the English version, I only need to look at the first, second, and third paragraph of
oh, I see what you mean.
Something like that. It's some hierarchical level.
So you mean in practice it's not true 1 million token? Maybe it's 100,000, this kind of stuff, and there is a way to filter and get the.
So we can say like 1 million.
Exactly, I'm paying for that.
The product application requires the quarter order. If we strictly computed all the attention strictly, but probably as you said, then
also the software next will be very flat.
Most of cases very fast and it works. That's why I think some sort of low rank approximation is working in practice.
Interesting.
But in the worst case, I think the whole token is still 1 million. Yeah, because
in the worst case.
If I just say okay, look at the whole paper, the whole sections. And ask me the one question for each section, so it need to
for the only task they are good enough at is to locate some information. Like if I get I know some very famous saying by a character, and I want to know which part of, for example, Harry Potter has this sentence. They can immediately get to know. It's very similar to Google, right?
So
it looks like a RAG. a little bit like RAG, you know. So you do a search, and then it's going to look at, you know, in your search in their database, what are the most relevant documents, and then they are going to append the most relevant document to your question.
But I think it's slightly more, it's slightly smarter than search engine, because in search engine you really need to remember what you want to search. It should be relatively accurate, but for large language model with 1 million context window, it can be some less accurate, and they can still still guess what you are looking for. But it's basically a combination of information retrieval and attention. It's not attention only. Attention only, you cannot really have 1 million context window.
The base task is basically the next token prediction, right? So if we link it to the next token prediction, then probably I think full attention is not required, and probably I think
yes,
attention is enough.
Yeah, if it is an n-gram, exactly, an n-gram answer, probably you don't need that. Yeah.
The attention is very flexible, so every next prediction you can changes the attention parts. And that's why it's very well fit to the natural language processing.
Yeah, exactly, absolutely. Yeah.
Very interesting. Like if you consider RAG instead of, you know.
Oh, we did that. We already did that. There is we already did the. So what is interesting, for example, what we do is exactly. So, for example, let's say you have a question which is related to Wikipedia. So if you ask directly, I think it was Llama. If you ask directly Llama, he can make mistakes, right? Because he has his internal memory, but it's very hard to get access to everything in his memory. So he's usually making stuff up. What we did is basically we have a graph retrieval that is going to extract the part on Wikipedia that is related to the question you ask. And then suddenly the performance is much better, because of course you force the system to reason with respect to the subgraph information of Wikipedia. Yeah. So
not but for like standard node classification tasks, if you can, you know, narrow down the n squared to transform as a coarsening step.
Yes. The point I work on this coarsening stuff for many years. It's very sensitive to any error. So if you lose the right information when you do the coarsening, there is no way you can get back the information. So I prefer something soft now, something like again, trying to get some kind of graph RAG, because if I make a mistake, it's not in the top, let's say the top 10 documents, but in the maybe top 100, it's still getting there. So by experience, yes, it would be much more efficient, what you are suggesting, but you need to trust a lot your coarsening step. That's one of the things. So yeah, it's a compromise here. Yeah.
So I have one high level question. I think the development of graph neural networks heavily rely on the development of like theoretical computer science topics.
Yes.
But how about the other way around? So the development of graph neural networks contribute to like development of theoretical computer science or network science.
Oh, that's a very good question. So this is something I was also very interesting. So when I started working on GNN, that was for two motivations. The first motivation was, so that was for molecules. Can we generate new molecules? Because molecules are combinatorial objects. So the space of molecules is huge. So are we able to capture in a vectorial space, right, molecules, and then we can increase the solubility or decrease the toxicity, and then we can generate new ones. And the second one is TSP, Traveling Salesman Problem. So TSP has been at the center of computer science for a very long time, because it has developed so many optimization techniques that we use every day, right? So can we go back to this fundamental problem and try to solve combinatorially this? So today the best solver for TSP is Concord, and he has used all the tricks in the book basically. So now what we are able to show that we are actually able to beat Concord, but for small scale, for less than 100 cities. So there is some way to learn this combinatorial object that was very surprised. So now the next step is to scaling up and everything, and then it's much more effort.
It's more like a learning meta heuristics.
Exactly. So
examples.
Exactly. So it's like it's possible to learn new representation of this combinatorial object, and I didn't think it was possible. So, but yes, it's actually possible. So this is the surprising case. Now formalizing, my God, it's going to take so much time. So it's more a proof of concept. Can we go back to this very hard problem of optimization, combinatorial optimization, and can we see some, interesting application of that? So that interesting new tools to solve this problem. So this is the part where I think it was exciting. Yeah.
Okay. That sounds great.
Yeah, and for example, so one application of that was for the genome reconstruction. So today, the way we reconstruct the human genome, so we have a machine, the machine extracts subpart of the human genome because it's too long, right? It's 3 billion sequences of amino acids. So the machine can only, take subsequences, but the subsequences actually they overlap a little bit. So this way you can construct a graph. And at the end, the problem that you need to solve is the longest path task, which is NP-hard. So we use that to reconstruct the human genome. So this is also going from the theory to application. So I think it's just the beginning. Yeah, it's going to be interesting.
Oh, great, thank you.
Thank you.
If the problem is NP turns out to be an NP-hard program, I think a practical algorithm is basically heuristics based over some greedy algorithm.
Exactly.
And that's why I also think that we can replace it by the data-driven method.
Yes, exactly. For the hard part. Yeah.
Okay.
No, people already did that. So for example, the mixed integer programmer, which is used everywhere in industry.
Yeah, that's right.
So DeepMind, what they did is basically, so they are inside the system. You need to start, for example, branch and discarding the branch, this kind of stuff. It's a heuristic that takes a lot of time to compute, but you can learn it, right? So you can have multiple instances, and then you can speed up your MIP system. And then for industry, this is very important for for anything like a supply chain or this. So my point is, probably this deep learning stuff will be very useful at some point, for this kind of combinatorial problem for industry. It's just finding the right, application of that.
On the exact algorithm, because it requires exponential time at worst case, and
yes,
it's totally not practical.
Yeah, but this is the worst case scenario. So if there is no structure, you're right. If you take, for example, TSP on random data points, but in the world, there is always structure, right? If you, for example, the Google map train from point A to point B, there is always structure.
Yeah.
So humans, we have a way to structure stuff even if we don't know, and then we can catch the structure with deep learning. That's I think this is the one thing I noticed. So if there is no structure, we cannot do anything. We just need to use the what mathematicians did before. But if there are structure, this is where deep learning can be useful, I think. Yeah.
So is there any other question? If no, so this is the our seminar. Thank you, Professor Bresson, for your presentation.
Thank you. Thank you for the questions. I'm very happy about this. Thank you.